All right. Hey guys, welcome back. We are going to chat a bit today. We're moving on kind of to the next chapter, and we're going to talk about increasing, decreasing, and piecewise functions. So in chapter 2, we're going to do, a bunch of stuff with functions. I think the title is like more on functions. So we're just going to kind of talk about the behavior of functions and how to describe kind of what the graph of a function is doing. And then we will kind of move on to the algebra of functions and then do some composition, which is just always a good time. So let's kind of, I just want to state a definition first, and then we'll look at some graphs. So quick definition, well, maybe not so quick. What's going on with my pen here? But a couple things. So let's let f of x be a function. And we'll just say, let's f of x be a function on some open interval. Okay, open interval, this is quite important. I need to switch pens. Okay, open interval I. Okay, so it's on some open interval I. Then we're going to talk about what this function is doing. So then we say that f is said to be, or is increasing, okay, increasing on I, if for all a and b in I, right? So for all a and b in I, if a is less than b, it implies that f of a is less than f of b. So all that means that so don't let that kind of confuse you. All this is saying is that if a is less than b, meaning as I look left to right, yeah, so I'm going to take a number that's less than the next number on the number line. If I'm looking left to right, then that implies that the function value that I'm looking at is going to be smaller than the next function value. So that kind of makes sense. Like if you think of if I asked you to draw a function that was increasing, I bet most of you might do something like this, right? And if you notice with a graph like this, if I take an a that is less than b, notice that the function value there, so there's f of a, there's f of b. So this is my f of a. Oh, that's nice and little. This is my f of b. Notice that f of a is less than f of b. That's what we mean by increasing. That's the definition of it. And notice to talk about increasing, we have to compare 2 points. That's going to be important. That's why we want an open interval when we list these intervals, because I can't talk about increasing or decreasing at just 1 point. I have to look over an interval. Later on in calculus, you'll talk about increasing or decreasing at just 1 point, but for now, we're just going to look at open intervals. Calculus is so great. F is decreasing. Really, what you see in calculus is it just makes describing functions much easier, and it kind of makes your algebra easier. That's what I love about calculus. All right, F is decreasing on I. So likewise here, if for all a and b in I, if I'm going left to right, that's all that a less than b means. This implies that now, what would I put here? Now instead of f of a being less than f of b, we want f of a to be greater than f of b. I want my function values to start getting smaller. And again, we can kind of see that. If I asked you to draw a decreasing function, maybe you would do something like this. So again, if I look at an a that is less than b, but then I look at the function value, there's f of a. And notice f of b is less than it. That's what it means to be a decreasing function. And hopefully this is intuitive also. You look at the graph either going up or going down, right? That's what we mean by increasing and decreasing. So it can be increasing, decreasing, or what else can happen on an interval? F is said to be constant, which that happens as well. We can be neither increasing nor decreasing. On I, if for all a and b on that interval, I don't even need to worry about going left to right. I just know f of a is equal to f of b. Okay, and again, I hope that's pretty clear. I would have a constant function That wasn't horrible. Here's my A, here's my B. Notice they are the same where they're supposed to be. All right, so 3 things that can happen to a function, a graph of a function that we're describing on interval, okay? Increasing, decreasing, or constant. Let's look at an example. Obviously, right? Of course we're going to do an example. All right, so this is going to just take me a minute. Let's see. Ooh, guys, those were really, really good lines. If you've been watching any of my videos, I think that might be the best lines that I have ever. Wow. I'm just going to sit and be proud of myself for a moment. There's nothing wrong with that. Wow. That's a great axis. I wish I could maybe like keep that forever, but probably can't, so that's all right. All right, let me do a couple things here. I just want to get kind of my points set up. And I want it to go like, ooh, sorry. Now I'm getting a little shaky. Not sure why. But let's look at something like this. Sorry, that's a little shaky. All right, so I want to list the intervals over which the function is increasing, decreasing, and constant. So I should have probably put that list. And this is going to be the graph of some function, f of x. Okay. List the intervals over which f of x is increasing. I'm going to be lazy, decreasing, and or constant. All right, so if we, look at our graph here a little bit. Now, when you're doing the intervals of increasing, decreasing, or constant, I need you to remember that you're only going to list the x values, okay? If you notice on our definition, it doesn't actually care what the function values are. All the definition cares about is whether your function values are getting bigger or getting smaller as you move left to right. So whenever you're listing these intervals, excuse me, of increasing, decreasing, and constant, you need to look just for where is my function getting bigger and where is it getting smaller. So as I look at my function here, my function values are getting bigger, 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 bigger up until about that point. And then as I move, so again, I'm looking left to right in my domain. As I move on in my domain, notice my function values are starting to get smaller, smaller, smaller until about here. Then they stay relatively the same until about here, and then you see they increase. So this is supposed to be -3 right there. So I would say if we look at this, sometimes I just say, okay, I'm increasing here, right? My function values are increasing as we go from the left. Over this interval right here, my function values are getting lower, so they're decreasing over that interval. What's happening here? I'm constant. And then from 4 on, it looks like we are increasing. So this is one nice way that you can kind of just, draw on your graph and see what you have. And then let's focus on how do we write this. So increasing, I'm going to use a capital I for increasing. Where am I increasing from? I know this is kind of weird because this line, it shows the arrow going down, but that just describes the behavior of the function. Really what that is saying is that, my function just, looks like this forever. So as I go from left to right, I'm climbing up the hill, right? I'm climbing up the hill, so I am increasing. Where am I increasing from? Minus infinity, because that's what we're assuming the behavior of the function is until -3. Open bracket, okay? Open bracket. I am neither increasing nor decreasing at that -3. I can't be both increasing and decreasing at a point, okay? So it doesn't make sense to include -3 because where would I include it? With the increasing or would I include it with the decreasing? Okay, remember our definitions, we're comparing function values. This is a hard one for my students to get. You need to keep this open. That is an open interval. We will talk about increasing or decreasing at specific points once you get to calculus, okay? And now if I look, where else am I increasing? So I increase from -infinity to -3. Again, those are x values. I don't care what the y values are doing. All I care about is, are they getting bigger or are they getting smaller? And then where else are my y values getting bigger? From about 4, from 4, although my graph isn't always perfect. all the way to infinity. Again, open parenthesis because I'm neither increasing nor decreasing at 4. At 4, I change from constant to being increasing. So am I constant or am I increasing there? I can't really say because I'm switching from constant to increasing. Let's look at decreasing. Decreasing is pretty easy. Looks like I'm just decreasing between -3 and 1. And then where are we constant? Constant, we're clearly constant from 1 to 4. Again, I don't care what the function values are. I just care that my function values are constant. I hope that makes sense. Again, always, 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 always open intervals. What do I mean by open? I mean you're never going to put a square bracket around those numbers when you're listing intervals of increasing and decreasing. Okay, I hope that kind of makes sense. There's also some other interesting things we can talk about. I'm not really gonna spend a whole lot of time on this, but we could talk about this guy being, we're not going to put this down as a formal definition, but this is called a relative max. A lot of times we care about where my function it's not the total maximum, right? Because this function keeps going on higher and higher. But we might want to know, let's say I teach business calculus, and what if we might want to know where we have like a little bump in our profits or a local maximum, or maybe I even care about a local minimum or a relative minimum. So we can describe functions like with a relative max or relative min, and we'll worry about that kind of later because we're not gonna do that right now. We'll talk about maximums and minimums a lot when we work with quadratics, and then when you get to calculus. This whole lesson apparently is wait until you get to calculus. It's just amazing. All right, so this might be kind of a quick kind of lecture, which will be unusual for me. Let's talk about piecewise functions. So piecewise functions can be a little bit tricky. They are exactly what they say. That's what you love about mathematicians, remember, is that if we say it's piecewise, it means that I'm going to define my function over its domain in pieces. Okay, so I am going to have a function basically that has a bunch of different pieces in it. So before we get to actually graphing them, let's just look at what a piecewise function is, and then we'll talk about graphing them. So let's consider the function. Piecewise functions are actually super. Piecewise functions are actually quite useful. 1 minus 4, let's say, so this is what the piecewise function makes me laugh because it makes me think like of something that can't make up its mind. So like me, sometimes I can't make up my mind on things. So this is what a piecewise function does. It doesn't have to make up its mind because we're going to define it in pieces. So let's say that this function is going to be, so it's kind of depends on where you meet this function. If you are on its domain and you're less than 0, this function is going to behave like the function 1 minus 4x squared. If you are between 0 or on 0 and 2, this function is going to behave like the constant 7. And then if you're on the domain where x is greater than 2, so you might see it like that, or I don't really like drawing it or writing it like that. I like to put my x first. And then if we're bigger than 2, my function is going to behave like 2x cubed minus x. So before we actually look at how to graph these, and this is a little much, we're going to just graph them with lines for right now, and then we'll worry about like graphing with parabolas and stuff later. But if what I want to do with this is I want to look at how we would evaluate. So what I want to do here is evaluate some function values. So like, let's say I have this function and I want to take f of 4. That's kind of big. I don't want 4, I lied. I want f of 3. Okay, so f of 3, what you want to do is you want to look at the value that you want to evaluate. I want to evaluate this function when x is 3, and you want to see which one of these inequalities 3 would satisfy. So clearly 3 is not less than 0. Clearly 3 is not between 0 and 2. So 3 is greater than 2, right? So this is going to be our winner. What I know then is I'm sitting in the domain, right, of x greater than or equal to 2. So what do I know about my function? My function is going to behave like 2x cubed minus x on that domain. It's not going to behave like any of these. Remember, you guys, this is a function. So for every input, there has to be one and only one output. That means there only has to be one place where that 3 is going to go. And that 3 is going to go in the place where it's defined on that domain. So in this case, f of 3, I'm going to look at this. I'm going to see 3 is greater than 2, so I'm going to plug it into this bottom part of my function. So I'm going to 2 times 3 cubed minus 3. Oh man, I'm not sure if this is right. It probably is. Arithmetic is not my strong suit. 27 times 2 is probably 54. Yeah, sure. Minus 3 is 51. What about f of negative 3? Okay, so f of negative 3, again, I look at this. I usually just kind of start at the top and see if it satisfies the first one. Is negative 3 less than 0? It is. So remember, the function doesn't act like any of these other two if we're on that domain where we're less than 0. So negative 3 is less than 0, so I'm going to plug it into this top function. 1 minus 4 times a negative 3. That negative 3 better be in parentheses, people, or else you're in trouble. Negative 3 squared is 9. 9 times 4 is 36. Please don't forget your order of operations. Aunt Sally would be so sad. I have an Aunt Sally. I always love that. I don't think they use that anymore, actually, very much in math, or in math classes anymore. What about f of 0? F of 0, so this is always interesting to look at where these break up. So, you know, if you look at your number line, right, we break up at 0 and 2, and here I'm going to be 1 minus 4x squared if I'm on that part. Here I'm just going to be 7. And here I'm going to be 2x cubed minus x. But I also have to consider, what about if I'm at 2 or I'm at 0? So if you notice, that's where these or equal to come in. Okay, so if I want f of 0, which one am I going to pick? I am going to behave like this second function here. The reason I'm going to behave like that is because x is equal to 0 in this case, and so I want to grab the inequality that, again, it satisfies. It just needs to satisfy that inequality. So what is my graph between 0 and 2? It's 7 no matter what. I don't really plug that 0 in. You know, if I had f of 1, it would be 7. Any number in that interval. All right, and then the last one, what about f of 2? So again, which one of these does f of 2 satisfy? It's going to satisfy this one right here because of my or equal to sign. So I would have 2 times 2 cubed minus 2. That's 2 times 8 minus 2. So 16 minus 2 is 14. Hope that makes sense. And as I'm looking at my notes here, I realized there was one more example of increasing and decreasing I might want to do, so we might come back. Sometimes I get a little cocky when I'm teaching and I don't look at my notes. So that's probably not good. Let's look at an example. How would we graph these? Let's see. So I'm going to graph a piecewise function. Let's look at f of x equals x plus 1. And let's have it be x plus 1 as long as x is less than 1. And let's have it be just 2x if x is greater than or equal to 1. Sometimes you'll see a 4x less than 1, or I think your book does that, 4 whatever, but this is, I believe, implied. All right, let's look at what's going to happen. So one way you can do this, that is a valid way to do this, is you could just graph both lines and then erase what you don't want. Remember, when you're graphing these, you better have a function. A function passes the vertical line test. If you graph something that does not pass the vertical line test, you have done it wrong, okay? This is a function, so for every input, there's one and only one output. So let's look at kind of what we can do to figure out what's going on here. So a lot of times what I like to do is just plug in numbers. So we know what a line is, we know it's slope 1, but let's just start plugging some numbers in. So let's start with this guy. I'm going to start with the one that is the or equal to 1. So what would f of 1 be? F of 1 is going to be 2, right? 2 times 1. And then I'm going to grab one more point that would satisfy this guy right here. Well, to satisfy this guy right here, I have to pick x values that are greater than 1. So let's get crazy and choose 2. What would f of 2 be? It would be 4. So I am going to actually graph that. I'm going to come over. So remember what this point is. This is 1, 2 then, and 2, 4. Okay, so I'm going to come over to 1. I'm going to graph to, oh, I didn't give myself enough room on my axis. It's doing so well. Maybe. All right, there we go. I didn't quite think about that when I went to graph. 1, 2, and then 2, 4. And then I know that this guy is going to go like this. Okay, oh, guys, can we, I'm going to change this a little bit. I want to change this a little bit. I'm so sorry about that. I just don't want them to overlap at this moment. They can overlap, it's fine. I just, for this first example, I don't want them to. Okay, there we go. Sorry about that. Oh, I used to hate it when my teachers did that. All right, so look at what I've done. I've graphed this part right here. I have graphed, and I've graphed it with this purple line right here. So now what I want to do is I want to go and I want to work with this side of the equation. Now, I'm going to put an f of 1. I know. Actually, I'm not even going to put in an f of 1 because I think that's going to bother you. It bothers me too because f of 1 technically is going to go into this guy. So what I'm going to do instead is I'm going to say, okay, so when at x equals 1, if I could plug it in, I would plug it in and I would get 1 minus 3, which is negative 2. But I'm going to tell myself that that's an open circle right there. So what we do, so I'm going to go to 1, negative 2. Now, guys, that can't be a closed circle. If that was a closed circle, then my function would not pass, it wouldn't be a function. I would not pass the vertical line test. But what I want to do is I want to use that open circle and I want to consider x equals 1 to talk about the behavior of x as we approach 1. So if I just went and I grabbed 0, which I do want to do f of 0, right? That's less than 1. F of 0 is negative 3. So I know I'm going to be down here. But if I didn't put that open circle there, notice I would miss all of those points right in this area right here. And then you could say, well, Sarah, why don't you just grab 0.5? Okay, well, then you're going to miss all the stuff between 0.5 and 1. What about 0.9? Well, you're going to miss, so you can see where I'm going with that. Remember, though, this is an open circle because I can't actually equal that function value at that point. So in mathematics, we use an open circle to really indicate I can get as close as I want to the 0.1, negative 2, but I'm never actually going to equal that y value of negative 2 because I already have a point at x equals 1. So there's my graph. And, you know, I would probably make sure that the graph is the same color. I just wanted to show you. So I have a line going up here. I have an open circle here, and I have a line going down here. Cool, huh? So just for the fun of it, what would my domain and range be? So my domain is going to be minus infinity to infinity. I can put in whatever x value I want. Doesn't matter, right? Where am I having some issues? At 1 maybe, but can I take f of 1? I sure can. I found out that was 2. What is my range in this case? My range is pretty interesting. I come from minus infinity, right? From all the way down here up to negative 2. I'm not including negative 2. Oh, Sarah, no, you're not including negative 2. I'm not including negative 2, guys, because this is an open circle. Then I skip all of these y values until I get up to 2. So I'm going to unite them together. I know that's kind of stupid, but that's really how I remember it's a union. I'm going to include 2 in this case because this guy is a closed circle, and then I'm going to infinity. So that would be my range. Where are we increasing and decreasing? We're actually increasing over the whole function, except maybe at that 1 right there because we're doing kind of some weird stuff at 1. But I think we could actually even include 1 as increasing. I should stop talking and think about that one for a little bit. Okay, let's do another one because these can be pretty tricky. Okay, I said this was going to be a short lecture, right? And now look at this. It's not. Let's do another one. Let's graph this function. F of x equals negative 1/3 x. I don't know what's going on with my pens today. Plus 2. 4. So this is what you'll see in your book for x less than or equal to 0. And let's do x minus 5 for x greater than 0. Okay. All right. So I'm going to just start with the top there. Make sure you have enough tick marks. I need to probably just like create an axis and save it and then copy and paste it each time. But that would be so easy if I were to do that. All right, let's look at this guy first. What am I gonna start with? Well, I have x is less than or equal to 0. So for the purple, I am going to start with f of 0, and that's gonna be a closed dot because it's or equal to. If I put in 0, I get 2, so I know the point 0, 2 is on my graph. Now you're gonna pick another number. I wanna pick a number, or can I also just say, so I'm at 0, 2. You know the graph of this function is a negative 1/3, or the slope of this function is a negative 1/3. You really could just go down and to the left 3 if you see your slope. You're welcome to do that. If you can see that this is a line and that it's just simple slope, you can go ahead and do your slope from that point. If you don't see that though, that is okay. X is less than 0. I need to pick a number less than 0 to put in this. However, I need to understand too, I need to look at this and realize whatever number I pick is going to be divided by 3. So why don't we think about it? I know, again, I'm asking a lot. I'm asking you to think. I'm going to put in negative 3 because I know negative 3 is less than 0 and I know that it's divisible by 3. So if I do that, I get a negative 1/3 times negative 3 plus 2. Those cancel. Oh yeah, that's going to be right. 3, that's got 1 plus 2. So what is negative 3? F of negative 3 is 3. So I know I have the point negative 3, 3. So when I did that, I should have gone up 1 over 3 when I showed you that earlier. Sorry about that. So negative 3, 3. Right, there's my negative 3, 3. Or again, and you know what's even better is if you can count. Sorry guys, I'm kind of fighting a cold here and it's making my head a little wacky. Never have days like that. Or again, I could have gone up 1 and over 3. Okay, so I'm going to connect the dots. La, 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 la. All right, cool. So we got that top graph done. Let's look at what's going to happen with the bottom one. I'm going to erase this so I have a little bit of room. So again, I'm going to choose points that make sense. That's always a good thing, to do things that make sense. X minus 5. Now again, if you can see what this is going to do, if you see you have a slope, or if you have a y-intercept of negative 5, and then you have a slope of 1, you're welcome to use that. But again, remember, look at this purple line. I didn't draw any more of it because this purple line is not the purple line if it's greater than 0. So right there, that's why we only have half that line. Same thing for this yellow one. Again, I'm going to look at when x is 0. When x is 0, y would be negative 5. If I could do that, I'm going to put a little circle here to remind me that's an open circle. And I'm not going to use the function notation, just to kind of remind myself too that I can't actually evaluate that. And then I'm going to pick a number that's bigger than 0. Just go to 1 or whatever. It doesn't matter. You can pick whatever number you want greater than 0. Maybe don't pick 92 because that might be difficult to graph, but pick a number. All right, so when x is 0, y is negative 5. 1, 2, 3, 4, 5. But it's not really negative 5 because we know at 0 it's 2. So we're going to do an open circle here. And then if I put in 1, I'd be at negative 4. Or I can also look, the slope of this sucker is 1, so I could go up 1 over 1 each time, up 1 over 1 each time, and so on and so forth. I do know it's going to go through there, so I feel like I didn't. Oh, my scale's a little bit off, which is going to kind of bug me, but that's all right. I hope it doesn't bug you too bad. There we go. All right, so let's look at this. This is pretty cool. If you notice, is it a function? need to worry about that. Does it pass my vertical line test? It does, right? Even on the y-axis here, that big vertical line, it only crosses at one point, which is the purple line. So it works. That's really exciting. Let's talk about domain and range. Our domain is minus infinity to infinity. I can pick whatever x value I want. My range in this case is kind of interesting. What's the lowest y value we take on? -5, and it's not equal to it. Oh, come on, Sarah. Not equal to it because that's an open circle here. So -5, and then remember, this guy's going to go up and grab every single y value after that. So it's -5 to infinity. Some interesting things if we wanted to look at where is this guy decreasing. It's decreasing from minus infinity to 0. And then after 0, we start increasing from 0 to infinity. Remembering that these are open intervals. They are always, always, always open intervals. All right, let's do one more and then we'll call it good. I'm not going to do that other example I talked about because I think I got what I needed to there. So let's look at this one. F of x. Doesn't always have to be f of x. I don't know why I insist on doing f of x, but whatever. Let's have it be 4 for x less than or equal to -2. I want it to be x plus 1 for -2, between -2 and 3. And then I want it to be -x for x greater than or equal to 3. Okay, cool. All right, so let's see what, again, I'm just going to pick one of these to work with. I'll just start with the top one and work my way over. 1, 2, 3, 4, 5, 6. I really do need to get one that my tick marks are not super regular, so sorry about that. All right, this one's easy. 4 for x less than or equal to -2. So f of -2, that's going to be a closed circle because it's or equal to. It's going to be 4. Give me a number less than -2. F of -3, what is it going to be? 4, because it's a constant function, so that's pretty fun. So at -2, I'm going to come up to 4, okay? And it's going to be a closed circle at I put -3. I'm going to be up at 4, and it's just going to continue at 4 all the way until we get to minus infinity, which we're never going to get to because it doesn't exist, because infinity is not a number. Let's look at this one. This one's a little bit tricky, but we're not scared of it. I'm going to look at what happens at -2. When x is -2, I know it's not going to be an open circle or closed circle. It's going to be an open circle. But when x is -2, what is -2 plus 1? -2 plus 1 is -1. Let's pick a number that is between -2 and 3, like 0. So what is f of 0? F of 0 would be 1. And then let's look at 3. What if, again, that's going to be an open circle, you guys. X equals 3. 3 plus 1, y would be 4. I know it can't equal it at those points, but I want to describe the behavior of the function. So when x is -2, y is -1, open circle. When x is 0, y is 1, and then when x is 3, y is 4, open circle. And then every point in between is technically a closed circle, right? Just gonna make that a little bit bigger. Every point in between is technically a closed circle. We just don't like say that, but every point in between is closed. Open, open, and then everything inside is closed. All right, and now let's look at the last one here, -x. So at 3, this is going to be a closed circle. F of 3 is going to be -3. And I want to grab a number bigger than 3. F of 4. It's just the opposite of that, -4. So I'm going to come over to 3 and go down to 3, closed circle. Then 4, go down to 4, closed circle, and move on. Again, if you see that these are slopes, you are welcome to, graph these using slopes because they're lines. And that's my piecewise function. Isn't that neat? I love doing piecewise functions. That probably doesn't surprise you at all. And when we get to like quadratics and stuff, we'll make these piecewise functions a little bit more interesting. Like we'll do an x squared, we might do an x cubed in them, so that I might get some cool looking parabola thing, once we get there. Really quick for our domain. Our domain again is minus infinity to infinity. Because we don't have any breaks right here. We can make these more complicated, but for now we're not going to. And my range, if you look at my range, we're going to go from minus infinity up to what? -3, including -3, union, and then we go from -1 to 4, where we don't actually equal the -1, but we do equal the 4 because we grabbed the 4 in the purple one. So that's pretty cool. Where are we increasing? We're increasing from -2 to -3. Not -3, +3. Oh my goodness, Sarah. -2 to 3. Where are we decreasing from? Well, we start decreasing at 3 to infinity. And then look at this one. This one's kind of fun because where are we constant at? We're constant from -infinity all the way up to -2. Again, all of these being open intervals. Said this was going to be a short lecture and I lied. I'm sorry about that. I didn't mean to lie. But I thought we'd get done well under 40 minutes and we're only like 5 minutes under 40 minutes. So it's a little bit shorter. If you have any questions, please let me know.